Okay, so for the main topic for today is going to be just kind of a general introduction to a certain framework that's typically used in the theory of reinforcement learning. I'm going to present my notes. And then, so basically this is I guess what might be called the Cartesian framework. For RL. And then I guess one thing to note is that I think a lot of interesting questions for AI safety is sort of questioning this framework itself. But we're not going to do that today. We're just going to present the framework, its kind of mathematical structure, and then in a homework try to explore some properties. So yeah, we're doing kind of classical learning theory here, and this is the typical setup for classical learning theory. So in this setup, we have an agent who has a policy. Then we have an environment. And then in this setting, they're kind of well separated, and then they have an interaction where the agent or the policy produces actions, and the environment produces observations. Yeah, so I guess the question is, are you using agent and policy synonymously here? I think the usual language is there is an agent who has a certain policy, but as far as we're concerned, for now, I think there's nothing more to the agent than the policy. So in that sense, we can use them synonymously. Sometimes in learning theory, it's actually called the learner instead of an agent. Maybe the agent is more of like a in the economics or the decision theory literature. This is terminology. So in terms of the kind of mathematical formalism, also it's possible that I'll miss some of the messages in the chat. So if there's something I'm not responding to, because I think I didn't hear a sound. So yeah, if I'm not responding to a question, just feel free to let me know that there was a question. So we're going to have a set A, which is a set of actions. In some fancier setups, you might want to make this a topological space or some other structure, but in its bare form, you can just take it to be a set. And then there's also a set of observations O. I think for as far as we're concerned for right now, you can imagine both of these just being finite sets. And then, so we build up the framework kind of gradually. First, we'll start with the deterministic setting. There's like a discrete time and deterministic. Setting. So in a deterministic setting, what a policy pi can do is take a history or a sequence of observations and output a certain action given the sequence of observations. So here, O star is, I guess this is sometimes called the Carini star. It's the set of all words on the observation. So it's the disjoint union of ON for n in n. So these are just finite words. So this is basically just, okay, here's the 3 observations that I saw so far. What is the corresponding action that the policy outputs? And the kind of dual thing for the environment is eta, it takes in a sequence of actions and outputs an observation. Any questions about this notation so far? So given these definitions, we can talk about the set or space of environments shown denoted by E. So this we can write as A to the O star. And this exponential notation just means what I wrote up here. So this is a set of eta mapping from O star to A. So this is a set of deterministic environments, and then there's a corresponding set capital pi of deterministic policies. And I guess even if, this is just an aside, we won't have to worry about this, I think, for now, but even if A and O are just discrete finite sets, then that's still fairly natural topology on these two.
Is E the set of environments or the set of agents?
This is a set of environments.
An environment takes observations and produces an action?
Oh, sorry, I read this the wrong way around. Sorry. Thanks.
Yeah, it's the other way around.
Yes, thanks. So this is a set of policies, takes observations, outputs actions. Set of environments takes actions and outputs observations. Yeah, thanks for that. These are environments. Anyway, I was just saying as an aside that there's you can put like a product topology on these. So, but I think for today, definitely we don't have to worry about that. Okay, and then I guess the kind of interesting part of this is that this can interact with each other. So there's an interaction. So basically what this interaction does is the notes, yeah, I can share these. Yeah, I can. Maybe I'll just put these in the Discord after the meeting. So for the interaction, can take an environment and a policy, and then from the two of them interacting, what we get is an infinite sequence of observations and actions. So this is O cross A to the omega, which is just a notation for infinite sequences of pairs of observations and actions. And here, so there's actually like multiple ways you could define this interaction. There's not really a canonical way of doing it, unfortunately. I write one version down and maybe say something about what else one can do. So here, if you take an environment eta and the policy pi, the corresponding, I guess these are sometimes called destinies, the infinite sequences of observations actions. Say O0, A0, O1, A1, and so on, is given by O0 is just the output of the environment on the empty string, which denote by lambda. And then let's say A0 is the output of the policy on the empty string. And then A1, I should say O1 first. O1 is the output of the environment given the first action, which was A0. And then A1 is the output of the policy given the first observation, and so on. So like the next observation is going to be the output of the environment on the first two actions that the agent took, and then A2 is going to be by O0, O1. So hopefully, I mean, you can write down a recursive definition, but hopefully this makes sense. So there's a question.
What character are you using for empty string?
I'm using a lambda.
Okay.
Yeah, just lambda is just empty string. So that's just when there's no input yet. So in particular, this the clean star includes the empty string. So that's the kind of initial input, which is just no input. So here I was saying, this is not the only way to define the interaction. So the kind of schematic picture for what I wrote here is that, let's say, we have the environment and the policy, and then they each start with no inputs, and then their output is kind of passed on to the next time step. So they kind of in this setting, it's the reason I picked this for now is just it's symmetric. And then you can kind of imagine in this setting, the environment and the policy kind of take steps at the same time, and then they see what was done before. But I should probably say that I wrote this down because it's a little nicer because of the symmetry, but often in the literature it would be people would be using the asymmetric version, which is like maybe I'll start a new page. So this side we can have an asymmetric version, which is maybe more motivated by, like, if you imagine the agent and the environment playing a game, then the way it works is that, let's say, the environment takes the first step, and then the environment produces an observation, and then the agent outputs an action based on that observation, and then the environment reacts to that. So we could have this. I guess one nice property of this is it's kind of more like a back and forth game. Something that's can be a bit inconvenient is it's asymmetrical. Like, you have to choose who starts. Like, does the environment take the first step? Does the agent take the first step? And I think, as far as I remember, there's no like consensus about this. It's just you make a choice based on what makes sense for the situation you're considering. But for today's lectures, we're going to work with the symmetric version that I wrote down. Also, I guess I should say that most often we kind of care about the asymptotic behavior of in learning. We care about, like, what does this policy do in the long run. So it ends up not mattering too much which model we use, because what matters is whether the agent figures out how to behave well in a certain set of environments. Any questions about this up to now?
Do we need to worry about the state and the connection between the state and the observation?
So we haven't talked about states yet, which is, I think it's one nice feature of this abstract setting. There's no states, but I will get to talking about states in probably in like five minutes.
Okay, sure.
So maybe they will answer your
So
question.
in this
So
deterministic
for now,
setting, the actions are enough to determine the next observations.
yes, and I guess it's deterministic in the sense that the policy and the environment are deterministic in that there's no randomization.
Yep.
Uh,
Okay, thanks.
okay, so yeah, this is just an aside to keep in mind that you can define the interaction in other ways too. And then another thing I wanted to say is that in a lot of settings, like in a lot of like reinforcement learning, so what I presented so far is sometimes called the lifetime setting, where we kind of keep the policy and the environment running forever. But sometimes it's useful to consider a finite time horizon. So let's say we pick a time horizon t, and then we can make analogous decisions where we can define environments up to time horizon t, which are, as before, there are a set of maps from sequences of actions up to time t, outputting observations, and then here, this is similar to the Kleene star, except it's just a disjoint union of an from 0 up to t. And then we can define the analogous policies up to certain time horizon. And then also we can define their interaction. So if you take a environment defined up to time horizon t and policy defined up to time horizon t, you get a sequence of actions and observations, and I guess technically you can extend it up to time t plus 1, just because at time t they still each produce an observation and an action. So this is a fairly straightforward generalization of the previous setting to just a finite time. I think, yeah, maybe I should say something. I'm using this notation for like the image of this map. So it sort of takes an environment and a policy and kind of pairs them or couples them together into a sequence of observation actions. I think this is also like, I don't know if there's a very standard definition. Sometimes people just write, I think sometimes people just write eta pi, like just write them next to each other instead of putting the brackets. But I'll try to be consistent about using this notation. All right. Okay, so this is this sort of abstract setting. And then I think Lofkush was asking about, okay, what about states? And then yeah, the idea is that you can use a certain set of states to generate, for example, an environment. So this will be, I guess, a definition of. So you can choose different names for this. One way to call them is partially observable deterministic decision processes, or POMDPs, which it's not a standard terminology, but it makes sense. But these are more typically called Moore machines. So this is a certain construction using a set of states that we can use to define an environment, for example. So the input data is a set of states, S. Then we have an observation map. Observation map. Call this O going from S to O. And we have a transition map. Tau from, so given a state and an action, it tells us what the next state should be. And then generally we also need an initial state S0 and S. So all of this data defines a POMDP or a Moore machine. And this, I guess, is an interesting aside. So these are named after Moore. These are certain kinds of finite state machines. And Moore wrote a paper on this in like the 1950s. I think it's called Gedanken experiments, which just means like thought experiments. I forgot the exact title, but on finite machines or something like that. So he was already kind of thinking about like, okay, here's a kind of black box machine, and we don't know how it behaves. Like, what can we learn about its behavior just by observing certain outputs of it? So it's actually pretty already at that time. Learning theory was not much of a thing back then, but I think Moore was kind of already thinking in terms of learning theory of like, what can we figure out about this black box machine given our observations. And then, so basically you can put together all of this data and it produces a deterministic environment. So it gives you, from this you can construct an ADA which takes in histories of actions and outputs observations in sort of the straightforward way where you have the machine, you started at the initial state, which has a certain observation, and then for each action you evolve the machine through the transition map, which gives you a new state, which has a corresponding observation. So that way for each finite sequence of actions, we get an output observation, which is the observation corresponding to the state you get by evolving the machine through those actions. Any questions about this definition?
I have a question. Is it supposed to produce only one observation or a sequence of observations?
So it produces one observation for each sequence of actions.
Okay. Next observation after the sequence. Okay.
Yeah.
Okay.
Yeah, maybe I can write down an example to clarify this. But maybe, I guess one thing I should note is that, so as I presented, this is just one way of generating environments. So like you can set up a certain machine and it gives you an environment, but it turns out this is sort of a universal, this is a universal example. A universal construction, in the sense that if we allow for an infinite set of states, then we can recover any environment whatsoever. For example, I guess I won't work this out in detail, but we can take the set of states to be the A star to be all words and actions, and then it has a natural transition map where you just concatenate, append an action to it, and yeah, using this construction, You can define the observation map from S to O to be just equal to eta. So for any eta, any environment you start with, you get an equivalent Moore machine in this way. So yeah, if you allow for infinite sets of states, this is a universal way of generating environments. But often we actually care about finite sets of states because those are, in terms of representing something on a computer, those are the more realistic ones. Okay, so maybe let me write down an example. Let's say we have two observations, 0 and 1. Let's say we have two actions, A and B. And let's say we have three states, A, B, and C. And then an example machine we might write down. So here's state A, state B, state C. And let's say A corresponds to observation 0 and B and C correspond to observation 1. And let's say on direction A maps to B, on direction A, B maps to C, and C maps back to A. And let's say on direction B, every state just maps to itself. So in this case, we have this machine, and we can actually write down pretty explicitly what the corresponding environment is. So it takes a word, a string of actions, and outputs an observation. And for each word, I guess this machine, let's say it starts in initial state A. So in that case, we get observation 0 if the number of A's is equal to 0 mod 3, and outputs observation or otherwise. So in this way, we captured this environment through this pretty compact finite representation of this machine with 3 states. Does this make sense? Any questions?
So this is like one very specific way. Like, well, this particular example is Markovian. In that the next state depends only on the most recent action. So my question is like, are non-Markovian environments going to be like an important topic in this course?
Yeah, so I guess as I mentioned, even though these are Markovian in the sense that the next state only depends on the last state and the last action, but it's actually like in this generality, it's not really a restriction because as I said, these are still universal because we can just have enough states to keep track of the entire history of actions. So in that way, yeah, it's like being Markovian is, in this sense, it's not in this generality when we allow for infinite sets of states, it's not it's not a further restriction. And I think later on we'll generally, because if you allow for infinite number of states, then it's also very hard to say anything about learnability because typically we learn by sort of figuring out what happens within that. And in order to like reliably learn that, there needs to be some assumption on the sets of environments that we expect. So I guess we'll get to that tomorrow what learnability means and what we mean by a hypothesis class and that kind of thing. But yeah, does it clarify?
Yeah, thanks.
And so, Gergely, W here is an action sequence, correct?
Yeah, W, I guess I use it for a word. It's a it's a sequence of actions. So it could be like something like A, B, A, B, B, A. And then this one has 4 A's, so it's going to output 1 as an observation.
Yeah, yeah.
Okay. Let me check if there's a question in the chat. Okay. I might have written equals, not maps to somewhere. Yep, probably right. That it's probably not worth correcting. Okay, so that was the kind of a general high-level introduction to deterministic environments and deterministic policies. But in general, we're also interested in the randomized or stochastic versions of these. So let's introduce these stochastic environments and policies. So maybe based on the deterministic case, maybe our first guess would be something like a randomized environment should be something that takes in a sequence of actions and outputs a distribution over observations. And similarly, maybe randomized policy would be the corresponding thing. But it actually turns out to be not quite the right generality, because let's say we have a randomized policy, and then in the first step we take some random action and then we receive an observation. Then in the next step, how we randomize our action might depend on what our previous action was as well as what the observation was. So because so let's say I flip a coin and I go out the door and then I observed that it's sunny, then in my next step I should take into account that I went out the door because I flipped a coin and I didn't stay inside. So a better generality is to take to allow for dependence on the random previous choice of that the environment or the observation made. So in this case, it would be O cross A star, and then okay, I should say something here. And pi would be near to U. And then here I wrote this kind of partial arrow, which is intended to stand for partial maps. And the reason these are only partial maps is that we don't need to define what an environment does. For example, on histories that cannot happen according to that environment. Or conversely, for policies, we don't have to define what a policy does on a history that cannot happen according to that policy. So these are these only need to be defined on the domain of histories H in O cross A star such that the probability according to that environment of that history is positive. So in the previous example, if I have a choice to like stay inside or go outside, but my policy is that I never go outside, then my future steps in the policy don't have to like define what I do if I have chosen the action to go outside, because according to my policy, I never take that action. Yeah. Any questions about this?
So I understand that we move from like complete maps, like total functions, to partial functions because we want to, we don't want to like decide what we're going to do in situations that are impossible. But why are we now using the domain of eta as like, why do eta now, both eta and pi now depend both on the observations and actions?
All right, so that's what I was mentioning before, is that because the past actions, let's say for a policy, my past actions were randomized. So it makes sense for future actions to depend on what my past actions were. Like we could have included that in the deterministic case too, but it was already determined. So like just in the deterministic case, based on the sequence of observations, there's only one sequence of actions that we could have taken. But in the randomized case, we might take different actions based on the outcome of a coin flip. And then we want to allow for the consequent actions to depend on the past actions.
Okay, makes sense, thanks.
Yeah, so I guess that's a good point, that an alternative way of defining a deterministic policy would have been to to also define it on where was it? To also define it on on like O cross A star to A, and have it be a partial map that's only defined on the ones that are compatible with that policy. But in that case, that would just make it slightly unnecessarily complicated. So in that case, we just wrote it as a complete map. But here, because of the randomization, to get the sort of most general setting, we have to include both observations and actions, and because of that, we have to do these partial maps. Any other questions?
Why does it matter the order of O and A when you're doing the Cartesian product?
It doesn't. I guess. Why did I write it this way? I don't know. I probably just flipped it because of the duality.
It's nicer. It's more symmetrical, maybe.
Yeah, I guess I was just because I guess in the way that I set this up, everything is symmetric, so I just flipped everything. And of course, the Cartesian product is symmetric, so there's no need for doing
it. Don't you need to define the probability that you wrote in blue? Don't you also need to depend on pi, or is it
right? So that's a good question. It would, so it would in principle depend on pi. Yes, but I guess the thing we care about is just whether the given observations were possible. So maybe I should say here, maybe I should say eta pi is positive for some pi. So like basically, if this history is possible at all, then the environment should know how to respond to it. Yeah, maybe this is a better way. This is more precise. Yeah, thanks for it. Okay. So, and then given this, again, we can define an interaction. So in this case, we have the space of stochastic policies, which I'll write as E sub S, and the space of stochastic environment, stochastic policies. And now pairing these, we get a distribution of destinies, so distribution of observation action sequences. And then, so here I wanted to mention an alternative definition, which has some nice properties. I guess because of these partial maps, this definition can be a little awkward to work with sometimes. So we write down an alternative. And it's motivated by this interaction setting, which I think it actually tends to be the kind of theme that ultimately what we care about is that we can couple an environment and a policy. So the alternative definition is that we define an environment, a stochastic environment eta, to be a certain measure on destinies, so on infinite sequences of observation action pairs that needs to satisfy a certain property. So
What is this notation? M of?
So it's Christian. So this is measures, and I guess it's maybe I should say
It's a probability measures or just measures?
just measures. So that that would be important that these are not normalized. And then I guess we take maybe the Borel topology on this as the as an infinite product. But yeah, so these are not necessarily probability measures. In fact, they're. Let me finish the definition, and it will be clear that it will be probably clear what is meant. So these are measures which satisfy that for any deterministic policy, already that's pi and pi d for deterministic. If you write C of pi, this will be a set of destinies compatible with pi. So it's the image of the pairing pi with any across the set of all environments. So this is a subset of destinies. So what this means is that these are the destinies, infinite observation action sequences that are compatible with this policy. Then we require that the measure of this subset C pi is equal to 1 for all pi. So basically this is and these are going to be called polydistributions. So poly pi on O cross A omega. So these are polydistributions. They can have a total measure that's not normalized to 1, but they have this property that if you restrict to a certain policy and the destinies that are compatible with that policy, then restricting to that we get a probability measure. So the value of the measure in that subset is equal to 1. And then the claim is that the space of these polydistributions is in bijection with the stochastic environments as we defined them as partial maps earlier. And one of the homework exercises is going to be to work this out in a finite time setting where it's a little simpler and we don't have to worry about so much about measures and topologies and things.
So this is kind of a measure over all environments relative to a particular policy. Is that correct? We're saying that the measure is 1 if we take the set of all environments paired with a particular policy.
So maybe one way to say it is this: we kind of take this property of the pairing, and we kind of flip it around to define environments. So this is saying the stochastic environment should be something that, when paired with a policy, outputs a distribution on destinies. So the way we do it is we define a measure on destinies, which is not necessarily a distribution, but it has the property that once you restrict to things that are compatible with a fixed policy, then we get a distribution, and that is the distribution that we get by pairing that environment with that policy. So basically,
we're trying to get at something like a distribution over environments here. That's what we're
distribution. Well, we're trying to define an environment as something that gives a distribution over destinies when paired with a policy.
Got it. Okay. Yep. Yep. And pi d here means deterministic.
Yeah. So
policies.
Yes. And I guess these are also deterministic environments. So there's within the destinies for any deterministic policy, there's a subset of destinies which are compatible with that policy. Namely, the actions are in accordance with what that policy said. And we're saying that when we restrict to any such subset of destinies, we should have a probability distribution. It's a
object at the top is what you're referring to as a destiny. Is that correct?
A destiny is what's here. It's in red. So yeah, these are sometimes called destinies, sort of infinite sequences of observation action pairs that are like, okay, here's the destiny. Here's how everything played out.
Got it. Thank you.
Quick question. So the interesting thing here is the only requirement, the consistency requirement, is to check your measure makes sense on deterministic policies, and that's automatically enough for it to be consistent in stochastic cases as well.
Right. Yeah, that's true.
Okay, that's pretty neat.
Point.
Yeah, that's counterintuitive, but that's cool.
It's a little counterintuitive, but maybe I can say as an aside that if you take a distribution over deterministic policies, you can map it to a stochastic policy, and in fact, this is a surjective map. So it's not injective, but it is surjective. So in this way, in some sense, you can think about a stochastic policy is picking randomly between a set of deterministic policies. So also I want to say that I think this alternative definition will be a lot clearer after working at the homework exercise, because there you get like a hands-on thing of like what this means, and then you get to show that these are the same as the partial map. So I think that will clarify it a lot more. Was there another question?
Why is this not injective? Is there an easy example?
Yes. Let's save that for the discussion session. I think yeah, that is quite interesting to see why it's not injective. But I wanted to quickly maybe finish today's lecture, and you can also try to work out an example for yourself. I think it's a good exercise to try to find, try to understand why it's not injective. Actually, maybe I'll include that in as part of the homework exercise. It's a small addition. Okay, so let's move on just for the sake of time. So as previously, we had a kind of a more concrete way of generating environments using the partially observable deterministic decision processes. We can define partially observable Markov decision processes for POMDPs, which will be the kind of stochastic analog of the Moore machines that we saw before. So here the data is again as a set of actions, a set of states. We have an observation map. And here you could make the observation map randomized too, but it turns out it doesn't, it's not actually more general. But the transition map is the main thing that we want to turn into a stochastic transition map. And then so we have an initial state or an initial state distribution at 0. And maybe as an aside, if O is an isomorphism, so the set of states is just a set of observations, and then we get an MDP, so Markov decision process. So the partial observable means that the states are not fully observed. You only get partial information about the state via the observation. So this is a POMDP, and as before, we can use this data to get a stochastic environment here. And yeah, so I guess the stochastic environment is, as a partial map, it's here it is something like this. And maybe you can, like, in order to see how this is produced by a POMDP, I can write down a kind of little schematic for how this happens. So let's say we have an initial state. and then a first observation and a first action, then we can condition this initial state by matching the first observation, and then apply the transition kernel to get a new state. And then if you have a new observation action, we can condition the new state on the on O1, I guess, the next observation, and combine, take the action and vary with tau, and so on. So this is the kind of way that a POMDP produces a stochastic environment in this sense. Okay, so AI depends on OI. Well, so when defining the environment, we just take it as a both the observation and actions are just inputs to the environment. Maybe you're thinking if we have a policy, then the policy creates a dependence on the observation and the action. Is that the question?
I mean, it's just that in the diagram you didn't show it like any dependence between observations and actions, whereas like it seems like you need to observe something to take an action, right? So I thought that there should be like an arrow between, well, I don't know, like O0 should map to A0, or like A0 should depend on O0.
Right. So that's what I was trying to say. If you want to include the policy in here, 'cause right now I just wrote down how to get an environment. I think you're thinking in terms of, okay, like we also have a policy and then we want to model the interaction. Then we would have to include the policy, and the policy would create a dependence between the observations and the actions. Okay, so we're at time now, so I'll end the lecture here, and then, as I said, I'll stay around for a little bit for any additional questions, and maybe I can also just write down. But if you need to go, feel free to go. Just write down some example of what a POMDP might look like. So it might be something like where we have just write down a small one with two states, A and B, and we might have something like, at each state we can take either action A or action B, and then maybe if we take action little a at state A, then there's a 30% chance of staying at A and 70% chance of going over to B. But if you take action B, then maybe there's an 80% chance of staying at A and 20% chance of going over to B. And similarly, maybe if we're at B, then maybe taking action A, we're guaranteed to stay in B. But if you take action B, then let's say there's 50% chance of going over to A and 50% chance of staying at B. But that's a small example of what a POMDP might look like. All right. Are there any questions about anything we talked about today?
A couple of questions. One just about the diagram. So here you have O0 is connected to S0 via this black dot.
Yes.
And does that just mean that O0 is determined by S0? Is that just what that indicates?
Yes, I didn't explain what this diagram means. If if we want to be precise, what this is kind of a conditioning. So basically, we start with an initial distribution and an observation, then we want to restrict. We basically update on this observation. So we kind of rule out all of the states which are not that observation. That's basically
Okay.
yeah.
Okay, and then after tau, we get another distribution of states,
All right.
and then you condition on some other. And where do the observations come from? They just.
Well,
come
that's
from-
just. I guess I was just writing down, and that's what Mateusz was asking too.
That's
I
a
was just
similar
writing down how
question
to
from Mateusz, yeah.
how to define this environment, and then the input to an environment is a finite string of observation actions. So that those are the
Oh,
so
okay.
we call this H. Then this is what H is, and I was explaining how to define this partial map, and it's a partial map because if we update on a certain observation, which is impossible, then we cannot actually do this. So that's why this is only partial.
Right. Okay, and I guess this is one of those long questions, so feel free to say you can't answer now. But what are the advantages of defining environments to not include states and to only think about observations?
Well, I guess
The
it's just
standard RL is to have states as the key part of environments.
sorry, what was the last sentence?
Yeah, because like in standard RL textbooks, the environment includes a state, at least.
Oh, really? Well, I think people talk about kind of model-free and modeled RL, and I think it refers to this distinction, but I'm actually not 100% sure right now. But basically, the kind of the model-free where we don't talk about states is it's more abstract. So the benefit of it is just what's the benefit of any abstraction is that basically you don't need states to talk about an environment. So it can be useful to forget about states, and then but as we saw, introducing states is sort of universal in the sense that you can always model something via states, but I guess you don't need to. So sometimes it's helpful to just think about the environment in the abstract. And I mean, maybe a particularly important point here is just that the symmetry is completely clear between the agent and environment in the kind of model-free version. But then if you want to introduce both like states of the environment and states of the agent itself, then you start getting into complication of like, okay, is the agent modeling its own set of states? And then you get into kind of questions of embedded agency, which are of course quite interesting. But in this kind of abstract setting, we didn't have to worry much about that. Does it clarify something?
I think, yeah, the symmetry, that's not something I explicitly noticed, but when you say it, that is elegant.
And yeah, symmetry is elegant, so that's kind of nice. But I would say they're kind of sort of one principle in math is that if you can abstract away something that you don't need, it's often good to do so. And then you can reintroduce it whenever you want to make something concrete. So that's sort of a high-level principle in math in general.
Yep, sounds good.
I see a question in the chat. The question is, could you do an agent being a function taking a side effect for function A to O, and an environment is a function taking a side effect for function O to A? Yeah, I guess side effectful means that it has some effect on a certain state. Is that what it is? Yeah, so I think okay. I'm trying to parse this question. So you're asking if we could model if I understand it, you're trying to model an agent as something that's allowing for a state. It takes a map from A to O, and then, or wait, was the A to O an input or the kind of signature of the entire function? Okay, so okay, maybe I think I understand it. I understand the question. So I think that's basically what I said about a POMDP or a Moore machine being universal. So when I said this is universal, is that if you take this set of states to be all histories, which is I think what your side effect would be impacting is just the memory. Like you remember what happened in the past. In that case, I think you can think of it as an environment that reads in the history, takes in the last action, and then outputs a new observation. Yeah, it probably works for the stochastic setting too. There too, I guess the corresponding kind of mathematical structure would be a POMDP. So it's kind of a randomized function that takes in the state and the last action and outputs a new random state. So it has a random. Actually, probably the impact on the state can be deterministic, and then is it true? Sure, maybe that is not true. So maybe if you allow for the side effect to be also randomized, then yes. Did this answer the question? Yeah. The effect on the state has to be random too. I was just thinking if you could maybe just randomize only the observed part of the state, but that actually like that is a thing that's called an RDP, called a regular decision process, where you only randomize the observations. So once you know all the observations, then you get you can determine the state. But in a general POMDP, the state would also be random. Yeah, if I understood what you said correctly, then what you described is basically a POMDP. Okay. Any other questions?
You're going to send the homework right now?
I'll send the homework maybe in the next hour. Yeah, no, I'll send it by email and maybe also post it on Discord.
Okay, thank you.
And Jorge, would you care to say anything about what we'll be covering next week, just to give everyone some context on what this is feeding into?
Yes, so I guess this is sort of a general introduction of like environments and policies. And then next week, we're going to talk about learnability and what it means for a policy to learn in a certain class of environments, which will also be kind of somewhat on the abstract level, and then 2 weeks from now we'll get a lot more concrete with a specific kind of situation of learning, which is bandits.
Cool. Cool. Well,
Yeah.
thank you, Jorge. Thank you so much.
Thank you, everyone.
Thank you very much.